The hypothesis for the segment was the emission spectra of lambda max is determined by the observed color of the substance.
We'll start off by defining some terms.
Emission spectra is a tool to measure the photons emitted by a substance. It produces a graph of wavelength in nanometers against intensity, or the number of photons emitted at a given wavelength. A peak or peaks are produced which are representative of the solution. The example shown is of a red dye solution. The lambda max would be the wavelength of red light.
In order to determine if the hypothesis is correct, we first have to determine what the data would look like if it was correct.
This is a sketch of what the emission spectra would look like if the hypothesis was true, and we tested green dye, red dye, and a 1-to-1 green and red dye, which would be visibly orange.
However, that is not the data we got.
The spectra for the red and green dye both present one lambda max, whereas the spectra for orange or mix showed two peaks with local maxes. The wavelength for orange light was emitted at a very low intensity, whereas the two peaks of the spectra showed local maxes very close to the lambda max of red or green dye. This does not support the hypothesis.
To understand why this is, we compared the solutions. We noticed that the number of peaks corresponds to the number of types of dye molecules in the solution. This explains why no peak appeared at orange. No solution contained an orange dye molecule. All solutions only had red and/or green dye, so only two peaks appeared.
Therefore, lambda max is most likely caused by molecular structure and the individual components of a solution, not the observed color. As shown, red, orange, and green dye have different molecular structures. These structures cause different wavelengths of light to be emitted and thus different lambda maxes.
Photons excite electrons on the particulate level, so the observable color will be the mix of all photons emitted by these interactions, and the individual colors produced may not be discernible.
An emission happens when an electron gets excited to a higher energy state, then falls back down to its ground state. The photon is the energy released as it returns to the lower state. Electron excitation works like stretching. As you stretch farther, you become more uncomfortable, and it is more comfortable to return to sitting upright. Comfort is favored over discomfort. In electrons, low energy is favored over higher energy. Potential energy is increased as the electron moves away from the nucleus because it is attracted to it. The energy produced by this is quantized and unique. It is affected by the distance the energy levels are from each other. This can be affected by things like number of protons, energy levels, or electron domains. Number of protons can affect the distance energy levels are from each other because as the number increases, the larger amount of protons act more strongly on individual electrons, pulling the electrons and the energy levels closer to the nucleus. This causes the distance between energy levels to decrease, and this lowers energy absorbed and emitted. As different dyes have different atoms and number of protons, this will cause them to have a different lambda max.